This might look like a boring outcrop of rocks at first glance, but it's actually one of the rarest and most beautiful rocks that I've ever had the pleasure of rock hounding. As many of you know from one of my recent videos, I went on a Geological Society of America field trip a few months ago to Enchanted Rock in Llano, Texas. And I talked about how this huge granite dome formed in that video. But the one thing I didn't talk about was the other reason this location is so famous, which is Llanite, a rare form of rhyolite that contains beautiful blue quartz that has made Llano, Texas a destination for geologists. So today we're breaking down what Llanite actually is, how it formed, why the quartz in Llanite is so blue, and whether you can find it anywhere else. So let's start with, what is Llanite? As I mentioned, Llanite is an unusual variety of rhyolite, and rhyolite is a silica-rich volcanic rock. It's the volcanic equivalent to granite. In other words, it's the same composition as granite, primarily quartz and feldspar, but it cooled fast at Earth's surface rather than relatively slowly below the surface. This is why the crystal grains in rhyolite are typically much smaller than those in granite. The faster lava or magma cools and crystallizes, the smaller the grains, because the ions don't have as much time to diffuse to different crystal nucleation sites to make big crystals, so they all just nucleate where they are, creating more and smaller grains. But the rhyolite itself isn't rare. When volcanoes erupt on continental crust, rhyolite almost always forms. So what makes this rhyolite special? Well, unlike many rhyolites, this one actually started cooling slowly at first, which allowed large eye-catching crystals to form before the matrix, or the rest of the smaller crystals surrounding the larger ones, solidified. In igneous petrology, we call this texture porphyritic, meaning that the rock has larger crystals that we call phenocrysts embedded in a finer grained ground mass. But that's also not the rare part. The part that's rare about Llanite is that these phenocrysts, the larger crystals within the Llanite, are made of blue quartz. Which brings us to the question, why is this quartz blue? Well, several videos ago I talked about how quartz, which is just silica or silicon dioxide, should actually be colorless if pure. It's just the impurities, typically metals like iron, that give quartz varieties like amethyst and citrine their color. And the same could be said for the blue quartz in Llanite, except it's not iron causing the bluish purple color of the quartz in Llanite. Instead, it's tiny inclusions of rutile or titanium dioxide needles within the quartz crystals. Titanium, like many other transition metals, can cause beautiful colors. Why? Well, in that video about what gives minerals colors, I explained what it is about metals that allows them to create such stunning colors. It essentially all comes down to electrons. When light hits a mineral, its atoms interact with that light. And in minerals that contain transition metals, light can excite the electrons in the d orbitals of those metal ions. And for an electron to jump from a lower to higher energy level, it absorbs a specific wavelength of light. And the color that we see that the mineral appears to us is actually the opposite, or the complement color to this wavelength that it absorbs. However, this metal causing color process that past Rachel just described occurs when the metal ion directly substitutes for ions within the crystal structure, which actually is not the case when it comes to Llanite. The titanium in this case is actually in the rutile, the titanium dioxide crystals or needles that are present as inclusions in the quartz crystals. So in other words, it's a mineral in mineral situation, not an ion in mineral situation, which apparently creates color in a different way. Instead of the metal ion absorbing certain wavelengths of light due to the excitation of electrons, the color in Llanite is actually due to a physics phenomenon called Rayleigh scattering. Rayleigh scattering occurs when light interacts with particles or molecules that are smaller than the wavelengths of visible light. So in this interaction, no energy is absorbed, no electrons are excited. In fact, the scattered light has the same energy as the incident light, the incoming light that hits the mineral. So when light interacts with the microscopic rutile needle inclusions within Llanite quartz, it is scattered. So why is it blue if all the wavelengths of light are scattered? Well, it's because the shorter wavelengths of light, so on the blue side of the visible spectrum, scatter more efficiently. Thus, to the observer, the quartz appears blue even though it's chemically colorless. And fun fact, this Rayleigh scattering phenomenon is the same reason that the sky appears blue. Okay, but why is this blue quartz thing rare? Well, it turns out that these inclusions only form in very specific cooling and chemical conditions. Recall that rhyolite usually cools fast at or near Earth's surface, which produces typically tiny crystals. But Llanite cooled slowly enough, at least initially, to grow crystals centimeters across, which is relatively large in the volcanic rock world. So in other words, this magma was likely stuck at shallow crust levels for a bit and lingered long enough for these phenocrysts of blue quartz to grow. And on top of having the right conditions for large crystals to grow, the magma chemistry also had to be specific, containing high amounts of silica, some amount of titanium, enough oxygen present to form oxides, and having a stable temperature window for the formation of needle-like inclusions. Change any of those variables and you don't get Llanite, you just get boring old rhyolite. And there's still a lot of ongoing research as to why there was titanium oxides present during the volcanic and magmatic activity that formed these Llanite rocks a billion or over a billion years ago, and why they formed as needle inclusions. There's a lot still unknown about this, so I'll link some resources down below if you want to dig deeper. And if you want to hear the entire 1.1 billion year history of the granite and Llanite in this region, then check out my previous video on Enchanted Rock and the Llano Uplift, which I'll link below. And if you want to go on a GSA field trip for yourself, they take place all over the country and even internationally every year. The next set of field trips will be associated with the 2026 GSA section meetings next March, April, and May. I myself will be signing up for many of these, so I hope to see you there. Links are below. And fun fact, you can find Llanite in certain places in Texas where it's actually free to collect. This outcrop where we were on this field trip was one of these places where we were allowed to collect, but beware, the Llanite is very hard and durable, so unless you have a really sturdy rock hammer or mallet, good luck getting a piece off. I think that's why they make it free to collect in some places, because it is so hard to collect. But do remember that removing rocks from state parks is not allowed, so if you're in Enchanted Rock State Park, you can't take those. And lastly, I know some of you guys are wondering, can you find Llanite elsewhere on Earth? Is it just in Texas? Well, not Llanite exactly, but you can find blue quartz elsewhere, like in Brazil, South Africa, and some places along the Appalachians in Virginia and North Carolina. But Llanite specifically, the blue quartz containing rhyolite, at least the type we see in Texas, is somewhat unique to Texas, at least to my knowledge. Let me know in the comments if you found anything similar elsewhere. And with that, thanks for watching, and I'll see you guys next time. Bye!